works out. Okay. Hello, everybody. So today's going to be the fourth number theory lesson, mine and Zen. I think this is the fourth out of the six. So after this, we've still got two more. Okay. So today I want to talk about orders, right? It's a pretty cool concept in number theory. And then how today's going to work is I'm going to be going over orders, and then I'll kind of like do a recap of the stuff we talked about before. And then after that, I've got like some practice problems that we can try. Okay. So first things first, let's do orders, right? We can start off with the definition. So if we think about it, if we have a number n, and then we have another integer a, right? I want to do a raised to some power. So I can do a raised to the power of x. I don't really know what that is yet. And then I want to analyze that under mod n. And again, mod n just means I'm dividing a to the x by n, and then I'm looking at the remainder, right? And the thing with orders is that I am specifically interested for when a to the x is congruent to 1 under mod n. Because a to the x congruent to 1 mod n has some pretty it has some pretty interesting properties, right? And then it'll be really useful if we can make use of these properties. Okay. I think the one thing that most people, in fact, everybody should probably notice when they see this thing of like a to the x congruent to 1 mod n, should be something like a to the p minus 1 is congruent to 1 under mod p. And that is what we know as Fermat's-Little theorem, right? Fermat's-Little theorem, it's pretty famous and it's also pretty useful to use in Olympiad math. And it's kind of related to orders. So we'll define order as the smallest. Whoops, I don't know why it's not writing. The smallest positive integer. Positive integer. X such that a to the x is congruent to 1 mod n. And that smallest condition is important, right? And the notation is that we can write x is equal to the order. So we write ORD, and then we have a subscript, right? So subscript n. So order n with respect, sorry, order, and then subscript n, and then we have a. Whoops, a, yeah. So x is equal to the order of a under mod n, right? And that is the smallest positive integer x, such that when you have a raised to the power of x, we have a raised to the power of x, that the remainder when you divide it by n is 1. And it's pretty useful, right? Because what do we know about a to the x? Oops. It actually is because if you imagine, right, a to the x, I'm just going to copy this, a to the x congruent to 1 mod n. And if we think back to basically modular arithmetic from, I think it's 2 or 3 weeks ago now, if we think back to modular arithmetic, we can actually square both sides. We can actually cube both sides, right? We can raise both sides to whatever power we want. So for example, if I raise both sides to the power of 3, I can do a to the x to the power of 3 is congruent to 1 mod n, right? Because we know that 1 raised to the power of 3 is still 1. In fact, 1 raised to any power still gives you 1. So that's pretty cool, right? Well, on the left-hand side, we have a to the 3x then, right? A to the 3x is congruent to 1 mod n. So if x is the order, then we can actually kind of do some interesting stuff like multiplying the exponent. We can multiply something to the exponent, and then that will give some interesting results, right? Specifically, if you just look at the thing I said earlier, where we have a to the p minus 1 congruent to 1 mod P. This is, I'm going to do it like this. This is by Fermat's little theorem, right? FLT. Well, what do you notice, right? Because if we look at X such that X is equal to the order with respect P of A, right? Then what we know is that, well, A to the X must be 1 mod P. And that's kind of like by definition, right? Because X is the smallest positive integer. Then we have A to the raised to the power of X gives you a 1. Well, then that's pretty interesting because we also have another one up here, and it's P minus 1, right? So you can imagine if I multiply, well, I say multiply, but if we raise both powers, raise both sides to some power, right? We can do A to the X raised to some power. I don't really care. I can raise it to the power of K, congruent to 1 mod P. A to the KX is congruent to 1 mod P, right? So then you can kind of compare KX with the P minus 1. Yeah. So you can kind of like think, well, maybe there's a case such that KX is actually equal to P minus 1, right? It'll be really nice if that was the case. Yeah, so I'm just gonna put a question mark here. Maybe that's true, maybe that's not. Okay. In fact, this thing actually is true, right? So there is a case such that you can do KX equals to P minus 1. And that also means that, well, X divides P minus 1, right? And if X divides P minus 1, let's think back to what X is. X is the order of A with respect to P, and that would divide P minus 1 for prime, right? For prime. That's pretty cool. So what we have here is actually called the fundamental theorem of orders. It's pretty cool. So fundamental theorem of orders. Wait. Yeah, so fundamental theorem of orders, and I'll state that theorem here, and then we can try to prove it together, right? So what we have is we have if A to the power of X is congruent to 1 mod N. Here X is just any positive integer. It doesn't have to be the order, right? Then that is equivalent to, or we have an if and only if. Why is my whiteboard not working? Okay, so we have an if and only if. And that is order of A with respect to N. Remember, N is the mod, right? That would divide X. Okay, you can kind of see how this result up here, right? This result up here. That's like a special case of the fundamental theorem of orders. So I think we can take about 3 minutes-ish to think about how we might prove this, and then I'll go over the proof with you guys. So remember, the important thing here is that there's an if and only if, right? So you have to prove both ways. You have to prove that you can go from here, go from this side to this side, right? If this thing is true, then that means the order divides it. But then you also have to go backwards, right? If you have the order divides it, then you must be able to go backwards. So yeah, let's take about 3 minutes to think about how we can prove this, and I'll go back and we can prove it together. Okay. Okay, yeah. I think that's about time. So I'm just gonna go over the proof of this theorem, and then hopefully afterwards we can do some applications of this theorem on some practice problems, right? So let's start with the proof. And remember, like I said before, this is an if and only if. So you see the double arrow in the middle. So we gotta go both ways. So the easiest way to go both ways is to go one way at a time, right? So let's focus on one way first. So specifically, I want to go backwards first because that side is slightly easier to prove than the other way. So right now we know that the order of A with respect to n divides x. And we want to go from this fact to this fact on the left, and that is A to the x is congruent to 1 mod n. Right. So how we might do that is, well, we can take this condition and we can write it like in some other way, right? So if order of A with respect to n divides x, we can write x is equal to k times the order, where we just have k, it's some positive integer. I don't really care about, right? Then we can just look at A to the x. Well, what is A to the x, right? A to the x will be equal to, that's not congruent, it's equal to A to the k times order of A with respect to n. And now you might notice, wait, that's pretty interesting because if you have multiply, like if you have a product on the exponent, you can kind of like factor something out, right? That is just equal to A to the order n of A to the power of k. I've just taken the k out. But wait, that's just if you look at it, if you look at this thing in mod n, what does that become? So by the definition of the order of n, sorry, the order of A, we know that A to this power must be 1 because that's the definition of the order, right? So that must be congruent to 1 to the k. And that is just 1, right? Under mod n. So just to recap, so the most key step, I believe, in this proof is this part here, right? This part just tells you, okay, well, I've written x as a multiple of the order. Then I actually use the order to give me like a 1 in the congruence. Yeah. So then from that point, I can just be like, okay, that just gives me a 1 to the power of some power. And I can just ignore that because 1 to the power of anything is just 1. So now we have the left hand side, right? We have a to the x is congruent to 1 mod n. So that's one side done, right? And now we go from the other side. Now we go to the other side. So the other side is just the opposite. So we already know, we assume we already know that a to the x is congruent to 1 mod n. And then we want to get from this fact to the fact that order of A with respect to n divides x. So now this is slightly trickier, but not that much trickier, right? What we're gonna do is gonna use proof by contradiction. So what is the contradiction here, right? So the thing I'm trying to suppose is not true is that I'm supposing, so for the sake of contradiction, I am supposing that the order of A with respect to n does not divide x. Now we can write this in some way, right? So we can write x is equal to order, sorry, k times the order of A with respect to n plus some remainder, plus some non-zero remainder, because we know that the order of A, it does not divide x, right? So I'm just gonna add that here. R is not equal to 0. R is some non-zero remainder. So now let's sub it back into this equation here then, right? Because we have the most information here. Let's try to sub it back in. So we have a to the x, and that is equal to a to the k times the order an plus r. Okay, we can just use our exponent rules as before, right? And we can turn that into a to the r times a to the order of n, a to the power of k. So all I've done is I've just taken out the a to the r. And then that was pretty similar to before, right? So a to the order a, we know from the definition that is just 1, right? So we just have a to the r times 1 to the some power. And this is taken on the mod n. So that is just congruent to a to the r mod n. Right, so what we have here is we have a to the x. So a to the x is this term, yeah? It's congruent to a to the r on the mod n, where r is this remainder that we have. R is non-zero. But wait, the problem is, what is like a to the x on the mod n? It's 1, right? Because that's the assumption that we have here. That's the condition we're given. So if 1 is congruent to a to the x under mod n, then 1 must also be congruent to a to the r under mod n, right? A 1 must be congruent to a to the r under mod n. But then hold up. This kind of like this is kind of similar to the definition of the order, right? The order is also a to the power of something. It's congruent to 1 under mod n. But r is not the order. Otherwise, if r is the order, if r is the order, then there wouldn't be a remainder, right? So r must be larger than the order, if that makes sense. R must be larger than the order of n. Sorry, the order of a with respect to n. Because if r was smaller, then, well, if r is strictly smaller than the order of a, then this thing wouldn't be true, right? Because order is the smallest. Smallest positive integer. And then if r was equal to the order, then it wouldn't be a remainder here. It would just be x equal to order of a times another integer times k plus 1. So now we have r is larger than the order of a, but that's also bad. Why? Because r is the remainder of the division. Yeah. Right? And division, the remainder of the division we know has to be less than the thing you're dividing by. So whichever the case, this thing here, so whatever the case is, this condition here cannot happen. Right? And now we have a contradiction. And that means the entire thing is wrong, right? Our entire assumption here is wrong. So that's a problem. And then that means this thing is wrong. So then finally it means that order of a with respect to n must divide the x. Okay. Yeah, that's just the proof for the fundamental theorem of orders. I think we can go and do a problem now, right? Where we just use this idea of the theorem of orders. So the first problem that I hope we can try is that, all right, problem 1. We should try to find O n such that n divides 2 to the power of n minus 1. Right, so 2 to the power of n minus 1, gonna find O n such that this thing is true. I think we can go for about 5 minutes. So we'll come back at 7:27-ish, and I'll go over the solution to this one. Okay, good luck. Okay, yeah, I think that's about enough time. So let's go back and I'll go over the solution to this problem. And also think since today there's not that much extra theory, so it's just orders, I'm thinking we can do more work on like trying to come up with the motivation to this problem, right? Because I think that's also very important to help you solve these Olympiad problems. So I think the first thing we should do when we get any problem is that, well, let's just try out small cases, right? Because there's a really easy small case that we can try, and it's just all the small values, all the small values of n, right? So let's try all the small values of n. We can do n equals 1. Whoops. Can do. What's happening? Okay, yeah. We can do n equals hello. Yeah. We can do n equals 1. And then what we'll have is we'll have 1 divides 2 to the 1 minus 1, which is equal to 1. So that's good, right? That's true. That's very good. So we found a solution. Let's keep going. So we can do n equals 2. 2 divides 2 to the 2 minus 1, which is equal to 3. That is wrong. So 2 is not a solution. N equals 3. 3 divides 2 to the 3 minus 1, which is equal to 7. That's wrong. And I guess you can immediately notice that if n is an even number, that's pretty bad, right? That's pretty cooked. Because if n is an even number, then the right-hand side, whatever this is, it's going to be an odd number, right? It doesn't matter what n is, 2 to the n minus 1 will always be odd. So you can't have an even number that divides an odd number. It's pretty bad. So you can kind of like immediately see that, well, n equals an even number kind of just doesn't work. So we can kind of skip n equals 4 and we go to n equals 5. 5 divides 2 to the 5 minus 1. That's 31. That's also wrong. N equals 7. 7 divides 2 to the 7 minus 1. That should be 127. And if you do your division, you'll realize that, wow, this is also wrong. 7 also doesn't divide 127. And I think by this point, right? So next into the 9 is like 5, 1, 2. It's already kind of big. You kind of don't want to do the small cases anymore. But you can kind of see, right? You try these small cases and it just keeps failing, right? You can never find another solution for n. So now you might start to think, well, maybe this is the only solution, right? Maybe this is the only solution that is possible. So then what is so special about this number 1? What is so special about 1 that makes it the only solution? One property is that 1 does not have a prime factor, right? There's no prime factors in 1. That's a special thing about 1. Maybe we can try to match our thought, match whatever we're trying to do to that property, right? Okay. And we also know that this lesson is about orders, and you can probably do this problem with orders, right? So what I'm going to do is I'm going to assume n is larger than 1, and then we'll prove that there's no solutions. So if n is larger than 1, we must have a prime divisor p that divide n, right? It doesn't matter what n is, every n will have at least one prime divisor. So then we know p divides n, but n also divides 2 to the n minus 1, right? So now we can write 2 to the n minus 1 is actually congruent to 0 under mod p. And we have mod p, that's very useful, right? Because what is the most important result about mod p? And that's Fermat's little theorem, right? So I'm just going to rewrite this as 2 to the n is congruent to 1 mod p. And that's good because we also know that 2 to the p minus 1 is congruent to 1 under mod p, right? This is by FLT. So now you have this. So now you got 2 of these congruences, but also you know that the order So 2 to the order of p with respect to 2. Wait, no. Getting my notation messed up. Order of 2 with respect to p is congruent to 1 under mod p. That's just the definition, right? Then we know by our theorem of the fundamental theorem of orders, right? 2 to the, this order must divide p minus 1. And this order must also divide n, whatever our n is. Okay? Whatever our n is. So then if this number, so because the order is just a number, if this number divides both n and p minus 1, then we know that it must divide the GCD, right? The greatest common divisor of p minus 1 and n. Because this order is just some common divisor of n. It can be the GCD, it doesn't have to be the GCD. But whatever that number is, if it divides both of these, it must divide the GCD of these two, right? And now comes the interesting part, because we know that p divides n, and that the GCD of p minus 1 and n must be smaller than the smaller one of them, right? You can't have a GCD that's greater than the number itself. So we know that GCD of p minus 1 and n must be less or equal to p minus 1, right? If it must be less than or equal to p minus 1. Okay, so now what if we take the smallest? What if we take the smallest prime divisor of n, right? We can take, let's take p to be the, let's take p to be the smallest prime divisor of n. That's actually really useful. Why? Because we have that the order of 2 with respect to p divides this thing, which is less than p minus 1. So now if we take the smallest prime divisor, then the order of 2 with respect to p must be even less than this smallest prime divisor, right? Because it divides the GCD, which is less than p. Oh wait, we also know order also divides n. So now that's a problem, because we have a number, it is less than the smallest prime divisor of n, but it also divides n. So that's the problem, right? So that forces order 2 with respect to p to be equal to 1. Right, we can think about this. Because if we have a number, it divides the number itself, right? If we have a divisor of a number, and it's also less than the smallest prime divisor of that n, of the number, then whatever this mystery number here is, it must be 1. Okay. So now we know this fact. We can go and basically like sub it back in, right? We know that 2 to the order, which is 1, must be congruent to 1 under mod p. So 2 is congruent to 1 mod p. And we can do modular arithmetic in that we can minus 1 to both sides. So 1 is congruent to 0 mod p. Now this is very cooked, because p is, what is p? P is at least 2, right? Because p is a prime. But then if p is at least 2, then this thing can't be true. Like, if you leave a remainder of 1 when you divide it by p, it can't be a multiple of p, right? So that is where the contradiction is. Right? So that is where the contradiction is. And if we trace all the way back, our assumption Our assumption was n is greater than 1. So this assumption must be wrong. So therefore, n has to be equal to 1 for this congruence to work. Okay. Ooh. That's this problem here. We go down. Yeah. All right, let's move on to the next problem. Problem 2. You want to prove that let's see, every prime divisor of 2 to the p minus 1. So we're doing a lot of 2 to the power of something today, right? Every prime divisor of 2 to the p minus 1 must be greater than p. Wait, no, sorry. I ordered it wrong. It must be less than p, I think. Let me just check. No, it's greater than. It's greater. Must be greater than p. Okay. Yeah, that's problem 2. So prove that every prime divisor of this thing must be greater than p, where p is some prime. Where p is prime. Cool. Okay. I think we can take about 5 minutes to think about this problem again. The idea is pretty similar to this previous problem. The idea is really similar to this previous problem in that we're taking the order. I'm gonna think about what possible values that the order can be. And I'm not gonna say that much more because otherwise I'll spoil the problem. So we can try this for about 5 minutes and then we can come back and look at the solution. Okay. Okay. Yeah, hello. So we're gonna be back and we'll go over the solution to this problem. Right. So when you think about this problem, right? When you look at this problem, where do we actually start? Because like it might be a little weird, right? Because we have every prime divisor of this number. But that's kind of something we don't really see every day. Where it's like you have 2 to the power of a prime, minus one, and you want to look at the prime divisors of that. And you don't see really like any immediate factorizations of this number, right? You can't really say, oh, I can factorize this into 2 brackets and then there's prime in those 2 brackets. Because I mean, sure, like 2 to the p minus 1 is the sum of all the powers of 2's before, but that's not really useful because it's all the sum of all the powers of 2's, right? So as always, what I like to do is I like to start with the small cases. So we can do p equals 2. All right, p equals 2. So 2 to the p minus 1 is equal to 4 minus 1, which is equal to 3. And the prime divisors of 3 is just 3. It is greater than 2. Right? P equals 3. Well, 2 to the p minus 1 is equal to 8 minus 1, which gives you 7. And once again, the prime divisor of 7 is just 7, and it's greater than 3. P equals 5. 2 to the 5 minus 1 is 31. And that is still, because 31 is still prime, and that's bigger than 5. That's a special case, right? 2 to the p minus 1 is not always prime. So let's just try one more, right? P equals 7. 2 to the 7, sorry, 2 to the 7 minus 1 is 127. And for 127, I actually don't know if it's a prime or not. Let's see. Okay. I don't think, yeah, right. So 127 turns out to still be a prime. But anyways, the point is that the prime divisors, the problem should be true, right? If you try the small cases. But in this case, they don't really tell you that much. Whereas if you look at the previous problem, trying the small cases immediately gave you like one solution, and then everything after it was just like doesn't work. This problem isn't like that. It's telling you to prove something. So maybe what we can do is we can set like an arbitrary prime, right? I'll call it Q. I can set Q to be a prime divisor. Q can be the prime divisor of 2 to the p minus 1. And we're just trying to prove that Q is greater than P. So that is a want to prove. If we do that, we're done, right? Okay. So let's write this in mod notation, right? 2 to the p is congruent to 1 under mod q, where q is on prime. And once again, because we know q is a prime, that is really useful because if we have mod of prime, then we have some really useful results, right? You might think we should try Fermat's little theorem. That is like a natural way of going. That is like a natural way of thinking about it, right? In fact, we can try it. So if we do 2 to the q minus 1 is congruent to 1 on the mod q. That is our Fermat's little theorem. From there onwards, you might be thinking, oh, we can use the strategy we had from the previous problem. We can do order to, with respect to q, divides the GCD of p and q minus 1. But from here on, you're kind of like, but I don't really know what to do next, right? Because you can't really use the strategy we had from before. Because whereas before we had n here, and we know that q, well, in last problem was p, but we knew that p minus 1, but p was a divisor of n. In this case, it's not, right? Q is a divisor of 2p minus 1, not p. So now you might be feeling a little stuck. So maybe we should go back and try a different approach, right? So this thing might just be a little not useful in this context. Well, FLT is certainly very useful, right? But it's not really useful in this context. So 2 to the p is congruent to 1 on the mod q. We can go back to the fundamental theorem of orders, right? Because this is an orders lesson after all. The order of 2 with respect to q, that must divide p. So now we have this kind of like, yeah, so now we have this condition. You might be thinking that that's a little sus, right? Because what are the divisors of p? Only 1 divides p and p divides p. So there are only 2 options for the order. So the order of 2 with respect to q can only equal to 1 or p. So now you think, wait, that's good, right? Because we can just do casework on it. Whoops. So we can split it into cases. So case 1, order of 2 with respect to q is equal to 1. Normally when the order of something is equal to 1, that's pretty cooked, right? So let's have a look at this thing. So if we have 2 to the 1 is congruent to 1 on the mod q, that will force 1 to be congruent to 0 mod q. And that is the same situation as previously. So if 1 is congruent to 0 mod q, then that forces q to be 1. But we know that q is a prime. So that is a contradiction. So this case cannot happen, right? The order of 2 with respect to q cannot be 1. So let's go to case 2. The order of 2 with respect to q is equal to p. That is our second choice, right? So how might we want to go from here? So we have q is, we want to prove that q is larger than p. So 2 to the order, this is congruent to 1 under mod q. And 2 to the q minus 1 congruent to 1 mod q. Whoops. Okay, let's see. I'm going to be live solving this as well. I'm going to be honest. But let's see how we might prove to go from here to this, right? Okay, right, yeah, cool. So what I wrote down here is actually FLT. And I like forgot about this part of the proof. I was like thinking about this part before, but it's okay. So we have FLT here. Well, what do we know? We know that the order of q, the order of 2 with respect to q divides q minus 1, right? So that is our fundamental theorem of orders. But wait, what is the order of 2 with respect to q equal to? In this case, it's equal to p. So p must divide q minus 1. So now you're like, okay, that's good, because we know that for something to divide another thing, it must be less than the number, right? So that just says q minus 1 must be bigger than or equal to p. Because if you think about it, right, if q minus 1 was actually smaller, than p, then p cannot divide that number, right? A divisor cannot be greater than the thing you're dividing by. So we're done here because q larger than q minus 1, larger than or equal to p. And if we go back to what we had before, we had that q was a prime divisor of 2 to the p minus 1. And through just our deductions here, right, we have arrived that q is actually just greater than q minus 1, which is greater than or equal to p. Okay, so we've done the 2 cases and we are actually done with the problem. Cool. We have about 6 minutes left. So I think I won't do another problem, but I will go over basically the strategies that we've used just as a recap, right? Go over the strategies that we've used to do these two problems. So firstly, what we did was we introduced the concept of orders. So then we went on to the fundamental theorem of orders, right? And the important thing here that we should take care of is the if and only if sign. So after we had that, we go down and we see this problem. So you see how the two problems we've done today are basically 2 to the power of something minus 1. Whenever you have a number theory problem where it's like a number and we have 2 to the power of something and a minus 1, right? You might start to think, well, maybe this thing is about Fermat's theorem. Maybe it's about orders like it is today, or maybe it's about Euler's theorem, right? If you recall, Euler's theorem is just a generalization of Fermat's theorem. So you see this. Well, obviously, the first case to any problem is to try your small cases. So after you've done your small cases, you will start analyzing the primes, right? Because, well, it's a number theory problem after all. So you maybe should start thinking about primes. And if you get it to mod a prime, then you can use basically the results we've talked about before, right? So we get it to mod a prime. And then at this point, I think the order is pretty much motivated because you have, well, you know that the order must divide p minus 1 and also n. And then p is also the prime divisor. So then you get to the step, so order divides the GCD. So now you can basically imagine if I try to vary p, right? Because n can have lots and lots of prime divisors. If I try to change up this value of p, I can actually control what the order is. Right? I can actually control what the order is. So why don't I take the smallest one? So that's where the motivation for the smallest prime divisor comes from. Right. Cool. So now after you've taken the smallest one, I think the rest kind of just falls in place where you can be like, okay, smallest, then that forces the order to be 1. And then from then onwards, it's a pretty straightforward contradiction, right? It's just that when the order is 1, bad things tend to happen. So when you're doing a contradiction proof, try to get something, try to prove that the order is 1, basically. And second problem, it's kind of like really similar. It's just some other work on the order, right? You want to prove it's bigger than P. So like we've done here, so we've done all the start deductions. We got to all the possibilities of the order, yeah? So then we do casework. Obviously, order is 1. As I said, it's pretty bad. So you want to eliminate that case, right? And afterwards, that's the case you want. And just using more properties of the order. So the fundamental theorem of orders, you can basically solve this problem. Okay, I think that brings us to the end of this lesson then. That's about it. Thank you guys for coming. Just gonna finish about 3 minutes earlier than supposed to, but I think that's okay.